Hello, my name is Andrei Ruzhikov, and I will be presenting my talk on shortest products for non-negative matrix mortality. Let's start with a classical problem called matrix mortality. This problem, given a finite set of n by n matrices, asks if there exists a product of these matrices equal to the zero matrix. It is known to be undecidable already for 3 by 3 integer matrices, and quite a lot of research has been done on the restrictions of this problem for small dimensions and small sizes of the matrix sets so that we obtain decidable special cases. In my talk, I will be, however, taking a different direction, and instead of restricting the dimensions and the sizes of the matrix sets, I will be restricting the matrices to be non-negative. This means that all the entries of each matrix are non-negative numbers. And in fact, it doesn't really matter what exactly numbers they are in this case. We only care if each particular entry is zero or strictly positive. And this means that we also can replace all strictly positive entries with ones, and we can assume that 1 plus 1 equals 1. This just means for us that a sum of two strictly positive entries is again a strictly positive entry. When taking this replacement, we get a monoid of matrices over the Boolean semiring. This means that we can consider it as a non-deterministic finite automaton. To be more precise, let's say that we have a set of M matrices and each matrix is an n by n matrix over the Boolean semiring, and we define a non-deterministic finite automaton which is actually a semi-automaton. So it does not have any initial or final states. It is not going to accept any language. It is just a triple of a set of states, which in our case will be just a set of numbers between 1 and n, a finite alphabet, whose letters correspond to the matrices in the original set, and the transition relation, which defined in such a way that the transition matrices of the letters are just the matrices from the original set we started with. So let's look at the example. In particular, in A1, the second row contains two ones, and this means that by the letter corresponding to the matrix A1, the state 2 will be sent to the state 3 and to the state 2. And the third row consists of all zeros, and this means that the letter corresponding to A1 sends the state 3 to the empty set. It is easy to see with this construction that the image by some word of every state is the empty set if and only if the corresponding product of matrices is equal to the zero matrix. So now we can fully replace the original problem we started with the new problem called NFA mortality. And given an NFA, it just asks if this NFA admits a word mapping every state to the empty set. We call such words mortal. The NFA mortality problem is trivially in p-space because we can just guess such a word letter by letter and then apply it to the whole set of states, letter by letter again. And it's also known to be p-space complete already for binary alphabet, somewhat unsurprisingly. And these facts already give us an advantage of going from the original matrix problem to the NFA problem, because now this means that for the original problem, which is not obviously decidable, we get this nice p-space completeness result. However, what I will be interested in my talk mainly are the length bounds on shortest mortal words for a specific number of states and letters. So by MT, the mortality threshold of NM, I will denote the maximum length of a shortest mortal word among all NFAs with N states and M letters admitting a mortal word. So the first simple observation that we can make is that mt of nm is at most 2 to the n minus 1. And the reason for that is as follows. Let's start with all states active in our NFA, and let's say we apply the dashed letter. Then we just follow the active states, and so state 3 will stop being active, but states 1 and 2 will keep being active. And now if we apply the dashed letter again, all states stop being active, and this means that all states are mapped to the empty set. What it means is that this word is mortal, and to now get the length bound on this word, it's easy to observe that in the worst case, we will traverse all the possible subset of states as active states, and there are 2 to the n minus 1 of them. So this is the bound in the general case. Now I will just very briefly mention some existing results. There are not that many of them. So first of all, it was known that for an exponentially large alphabet, this upper bound is actually tied, and also that the lower bound for constant number of letters is already exponential, but it's, as you can see, quite far from the upper bound. With some more advanced constructions, it's possible to get a better lower bound, but I will not stop on this lower bound that much because we will obtain even better lower bounds just in a second. So the contribution of my talk are the following results. So first of all, I show that for the case of just n letters, the upper bound that we just discussed is tight. And then I consider the case of constant size small alphabets. So for 3 letters, the lower bound is as follows, and for 2 letters, it is slightly smaller, but still quite close to the upper bound that we have for arbitrary alphabet. And the way I do it is by simulating a binary counter. Okay, now to be more serious, let's discuss in more details the how the constructions work. So as I said, we're simulating a binary counter. And the way we do it is we look at the states as digits of our binary number going from left to right. And if a state is active, so if some state is mapped to this state at this point, then we assume that the digit of the number is 1, otherwise we assume that it is 0. So we start with all states active, so we have 4 ones in this case, and let's say we fire the transitions corresponding to the letter A4. So in this case, it kills the state number 4, and all the other states remain the same. So we get the number 1110. So we decremented our binary number by 1, and now we will fire the letter A3, which sends 3 to 4 and keeps everything else in their place. And the result of it is that now we get the state 4 active instead of 3, and once again we decremented our number by 1. So now we do that again to get rid of the state 4, and now to further decrement our number by 1 again, we apply letter A2, and we obtain the number 1011. Now you might ask what stops us from applying letters that we're not supposed to apply that would decrement the number by more than 1. And the reason is that there is a part of the transitions that I didn't show you yet. So for instance, if we try to apply A3 while the state 4 is active, then all the states will become reactivated by going from the active state 4 to all the states of our NFA. And as a result, we end up back at square one, and we would have to start the whole process of counting down again. So this intuitively guarantees us that the application of each letter decrement the number that we're encoding by at most one, and so the length of the whole word will be at least 2 to the n minus 1. And as we have already seen, this is an optimal bound. Now, to simulate a binary counter with a constant number of letters, the constructions have to be quite a bit more advanced than what I've just described, but the intuition behind them is very similar. So what we do is we define three letters S, C, and D. So S stands for shifting letter, and as you can see, its action is just shifting everything to the right until some point, and then if we shift too much, then the right half of the state set will be reactivated. So I should say a couple of words about the state set. Intuitively, we will still have zeros and ones in the corresponding positions, but now we have the left half, which will start with all zeros as soon as we do enough of shifting, and then the right half will actually contain the number that will be um, decremented. So this is precisely the reason why we have over 2 in the exponent of this lower bound, and additionally we have a state f, which as you can guess will be just a flag. So the action S, as I already described, uh, is used for pushing the number to the right until we have some zeros at the end of this number. But as soon as there is one and we try to push it to the right, it will just get back to the whole right half being active, and so we get back to our approximately 2 to the n over 2. So we'll have to start the whole counting process again. Now we go to the second letter, which is C, and C stands for check-in. So what it checks is just that the left half was completely cleared out. So it checks intuitively that the number of shifts that we performed was enough. If we try to apply this letter too early, then everything will be reactivated. And just to mention, so the bold arrows incoming into a state mean that this state is becomes active if at least one state was active before the application of C, and the outgoing bold arrows mean that if this state is active, then all the states of the NFA will become active after the application of C. So uh, now we go to the third letter, and this is the letter that will be doing all the heavy lifting. It's called D for decrement. And as you can see, what it does, it removes the last digit. So if the digit was 1 in the right half, it will become 0. But also it moves the number to the left half. And if you recall from the definition of C, we would have to move it back. But the reason why it happens is that now we also remember in a special bit the number of shifts we did with the letter S, and as a result we do the decrement precisely by 1, but now our number is floating somewhere in the left side, so we will have to shift it to the right side again. So let's look at some example. We start with all ones. And as I said, first we just shift everything to the right, obtaining this number, and then we can apply the letter C that just clears the lost state for us. So it will be 0. But now we get this 1 in the left half of the construction, and this one will be remembering how by how much we shifted our number. So in this case we just shifted by 1, so this one also will move by 1. And then when we're applying D, we have 3 ones here, so 2 of them will travel to the left, and then the last digit is switch to 0. So we did our decrement, but now we get this additional 1, which came from P1 actually. And the reason we have it is so that when we're shifting our number or our representation of the number to the right, what we're actually doing, it cannot harm our number. So then we would have to again apply C to remove this additional 1, and then when we do that, we will once again get a 1 in the left half, and so we will not lose the whole length of the encoding of the number just by shifting it too much. So this is more or less the intuition behind the construction. And for the case of 2 letters, the construction is very similar, but now because we only have 2 letters, we have to, instead of just having 2 sets of states, we have 3 sets of states. So we have the left, the right, and the middle part, but the actions of them are very similar to the 3-letter case. And again, you can see a very similar picture as an example. We start with all ones. We can shift them to get to the right part, and then we are applying the decrementing letter that decrement the representation by 1, and also adds the additional bit that will be looking after the length of the representation. Then it can be shifted to the right, and because this bit is here, it would actually have to go to the middle part, otherwise everything will be reactivated and we will start counting once again from the very beginning. And as soon as it gets here, we can again apply the letter D and continue the process down to 0. Um, but of course, no one likes to listen to other people's solutions. Everyone likes solving problems by themselves. So let me get to the good part, which is open problems. So the most obvious open problem is finding upper bounds on the case of constant size alphabet, and to the best of my knowledge, no better upper bound than 2 to the n minus 1 are known even for this case. The next interesting problem is finding classes of matrices or classes of NFAs where the mortality threshold is bounded by a polynomial in n and m. So I am aware of only one such example. This is unambiguous NFAs. And in this case, it was shown that the upper bound is n to the 5, regardless of the alphabet size. And another interesting open problem, which is quite vague, but I believe that it's quite interesting, is finding any algebraic properties telling us something about either the mortality threshold or maybe just um, the telling us about the answer to the decision problem, asking if the NFA or a matrix set admits a mortal word. And of course, one has to be careful asking this question in general because the decision problem is space complete in general. But for example, for unambiguous NFAs, a mortal word exists if and only if the joint spectral radius of the matrices of the letters is strictly less than 1. And this is, in my opinion, a very good example of turning a very combinatorial problem into a linear algebraic one. And this way it makes it actually very solvable very efficiently. Um, so it would be very interesting to see any other examples of this interaction, because as you could see, all the lower bound that I discussed are very purely combinatorial. And now, finally, I would like to mention a kind of toy problem, which is open. This means that it's not such an easy problem, and it concerns DFAs, so deterministic finite automata, instead of non-deterministic finite automata. So basically what we can ask is, given a partial deterministic finite automaton, what is the mortality threshold for this class, depending on, again, number of states and number of letters. And it is known that in this case, the length of a shortest mortal word, if it exists, is at most n times n plus 1 over 2. And it's actually reached by a partial DFA with n states and n letters. You can see it on the screen. And what it does is essentially just bubble sort. So it kills state 5, then we can send state 4 to state 5 and kill it, and so on. And this way it's just the number of swaps, so the sum of the first n natural numbers. However, what is interesting with this problem is, again, the case of the constant size alphabet, and this is something that keeps being quite mysterious and quite difficult to study, because what is known is a lower bound which is asymptotically about twice smaller than the general one, as you can see. But the tricky part there is that it's not even known what should the actual shape of this lower bound be, and there is no good conjecture for that. So the construction for the best known lower bound is pretty tricky and has a rather unstructured form, I would say. Here is a slightly worse construction, which has a bit more structure. And the idea here is that it's very easy to kill all the PIs, and after that we will be just sending all the QIs one by one to this line of P's, and killing them by getting them to P4 and then applying the dashed letter, and in the process we will have the rotation of QIs synchronized with the PIs. So, as I mentioned, we have this lower and upper bound that you can see on the screen for the mortality threshold for binary partial DFAs, but we have no idea what is the actual value. And while the gap between the lower and upper bound might look very small, in my opinion, it's sort of more of a structural problem. We don't understand what exactly happened there. And because of that, it's not so much that we want to make the gap smaller, it's more that we want to understand what properties make the mortality threshold of a particular DFA large or small, and there are very few tools to deal with it besides just the straightforward combinatorial approaches that people take. And in particular, to make a conjecture, just to make this thing a bit more active, I conjecture that the upper bound in the binary case can be improved, but I have no good reason to state this conjecture besides just guessing. And this will be the whole of my talk. Thank you.